So I just want to start with answering some, continuing on some questions which were asked in the last lectures about the property of the quasi-associator, before we start with the general theory of the quasi-associator. So the first question by you was about relation with braided monoid categories. And so here is the answer. So here, this is the formalism for infinitesimally braided monoidal category. So what is, so maybe we start with the notion of a braided monoidal category. So braided monoidal category, it's a category here with a bifunctor tensor product here, a braiding beta, which is a natural transformation from the tensor product to its opposite, which shares some properties, and associativity constraint, which is also a natural transformation between two functors from C cubed to C. One of them takes xyz to x times y and then times z, and the other takes x times z to x times y times z. And this is a natural transformation. So we have two natural transformations, and these two natural transformations should satisfy some axioms, which are so the axioms of braided monoid categories. And these axioms ensure that there are going to be braid group actions, pure braid group actions on any tensor product of n on n objects, so on x1, xn. So if I take any tensor product and C of this, so iso sub C, there is going to be an action of the pure braid group of n strands. So this is going to be a result of these axioms. Okay, and here similarly, there is a notion of infinitesimally braided monoidal category, so which is similar. So you have also symmetry, so commutativity and associativity constraints, and plus an extra structure. So first of all, the symmetry, the commutativity constraint here should be symmetric, which means that you have CYX, CXY is identity, which was not a requirement beforehand. This was just braiding and not symmetry. And the additional structure here is what we call infinitesimal braiding, which is this TXY, which is endomorphism of C of X times Y, and which also satisfies some axioms with respect to tensor product. Then the main, so you can say that the main feature of associator, so in fact, what the KZ associator is going to do for you is convert one into the other by the following formula. So in fact, we should put that this braiding is this commutative constraint times this exponential, and this associativity constraint is going by the old associativity constraint, which you multiply by the associator. So that's the way you go from one to the other. And so in fact, it's a deep property of associators, and in fact, you can recover in some way associators from these conditions, in fact. And this is what we are going to explain about associators. Another feature which is quite related to it of the quasi-associator, which I also want to explain, is that, which is in fact, which we can guess from here, is that an associator, the quasi-associator gives rise to braid group morphism, so representation of the braid groups. So here, this is a pure braid group in n strands. Here, this is this Artin generator here, I plus 1. And on the other hand, you have the Conodrin-Fadley algebra, which was introduced in the lecture, previous lecture, of which you have here the presentation. And the point is that you have a group morphism from Bn to this semi-direct product of X Conodrin-Feld times Sn, given by this formula. So this formula you can find in Drinfeld already. And in fact, you see here the role played by the quasi-associator here. So this formula seems a bit mysterious here. And in fact, they have to do with parenthesizations. So basically, for those who know, so it's the fact that we are here looking at 1, 2, 3, etc. n, and we are doing the following representation, so which explains why, in fact, so this 1, 2 is just mapped to this, and then you need associators in order to take the image of the other generators. So here you have another connection between, so another property of the quasi-associator, and it's also, in fact, general properties that will be shared by all associators. Okay, so in fact, I hope that this a bit clarifies, or I hope that this complements some properties of the Casey associator, which were explained in the previous lecture. So now let me go to the my lecture. So in this lecture, so I want to start the purpose of it is to explain associators. So the main result that there is a notion of associator, a scheme of associators, and this scheme of associators is the torsor over two groups, which are the GT groups and the GRT group. So these are the main results that we are going to explain them. So before that, I want to explain some things about formality isomorphisms. So in fact, you see here, so just to derive this, so in fact, if you look at this, this is just a morphism. This is just a morphism, but in fact, it's from here, you derive a morphism from a pure braid group to X of Tn, a group morphism, and in fact, there is a notion of Malchev completion, and you can, in fact, show, so let me write it here. So it's defined over C. It's over C. And you have the Malchev completion of Pn over C, so Pn of C. And in fact, this gives an isomorphism. So in fact, it gives a way of computing the Malchev completion of this group here. And so this is no accident. There is a general way of computing Malchev completions of fundamental groups. And this is just an example of this general results of computing Malchev completion of fundamental groups. So this is where I start. So here I'm going to explain about Malchev completions and about how connections are going to give us such isomorphism. So let me start the presentation. So I should, okay, so let me start here. So here there is, okay, so here there is a notion of, is there a beam? Okay, so here we have, we start with gamma affinity this group, and there is the notion of, so the Q gamma is its group algebra. There is a notion of its completion, so which we define in A. So we quotient by the powers of the augmentation ideal. And so this is a complete Hopf algebra. If we take its primitive elements, this is so the Malchev-Lie algebra associated with gamma. And this, in fact, this group here is the exponential of this Lie of Pn. Okay? So in fact, this Malchev-Lie algebra, Lie of gamma, it's an invariant of the group that you would like to compute. So in fact, there are other things that you can associate in C and D, so graded things. And here, in fact, this is, in fact, lemma 02 gives a technical result how to compute Malchev. So you see, this Malchev-Lie algebra is just filtered Lie algebra. And so the question is to make it isomorphic to a graded Lie algebra. So T and here, C is a graded Lie algebra. And the question is when, so how do you construct an isomorphism from between graded and filtered? And so here in lemma 02, there is such a way to construct such isomorphisms, because here you start with a group of gamma from UA, from G to group-like elements of UA, which satisfy some conditions. And so if you do that, this gives for you an isomorphism Lie algebras between Lie gamma here and A hat. Okay, and here is a proof. Yep. La croix qui est là? La croix. Ah oui. OK. Thank you. Voilà. Okay. So here we see a proof. So in fact, you can it's uploaded, so you can check it. But in fact, what is interesting is that it gives you a criterion how to construct such isomorphism. So in fact, if you have a group morphism, so here is the main thing here is here. So this is morphism from gamma to UA hat. So this group-like elements, and from there you get these isomorphisms of Lie algebras. Okay, and then in fact you can say so how to construct such things. So assume that you have a manifold M, and then A is this positively graded Lie algebra, and then you have the so-called notion of Mohr-Cartan element. So Mohr-Cartan element is the element J. It's a one form in M with value used in A, such that dj equals 1/2 of jj. So so it constructs for you a flat connection d minus j over a trivial bundle over A, and of it you can take the monodromy representation. So in fact, the question is when such an element j gives you a monodromy representation such that it will give rise to the morphism of Lie algebra that you are that you want. And here is the criterion. It's lemma 0 form. So here you take a starting point M in B, which is a starting point for your representations. J is this Mohr-Cartan element. And then, so here, the first are the technical conditions. And then the thing is that you are going to apply this lemma using the group morphism induced by integration of this flat connection. And then, in fact, this computes for you. It tells you that if you can compute with this particular Lie algebra A such a Mohr-Cartan element, then you get this formality isomorphism for the fundamental group of M. That's the point. In fact, you can also do this. Great. And so you can do this also in a situation we have not just a base point, but a whole bunch of base points, and so you don't have a fundamental group, but fundamental groupoid. So here, where is it? Okay. Okay. So here in this lemma 06, you see the analog of this. So when you have a subset in M, and then you do the same with a groupoid isomorphism. So just a stupid generalization. And also you have variants where you have also group actions. You can assume that you have an additional group action. So all this will be useful. And in fact, I want to remind you of the fact that if you in this situation, so you can do, for example, out of this data, you can construct orbifold fundamental groups. So, for example, if you do, it's a typical example of this situation is when you have, for example, you have the configuration spaces. So, in the situation of configuration spaces, then it's a situation where you have these endpoints on C. Okay, and then you can take this C bracket at of C. And so you can do, for example, if you have a particular element B here, so you take pi 1 of with respect to B. This is a pure braid group, but you can as well take loops paths going from B to sigma B. and then sigma being an element of the symmetric group. And you can put together all these elements for all sigmas belonging to Sn, and then you construct out of this the braid group, in fact. Okay? So, in fact, you have the situation of, in fact, a group OX leading to groups. Okay? So, it's an example of what is written here. Okay. So, let's continue with this presentation. So, now there is a notion of tangential base point. So, what is tangential base point? In fact, you will assume, so for example, we will need particular base points on this configuration space of endpoints on C. And what, so in fact, here you have the example. The example is here. So here, M is here. You have this Conodrin-Feddy algebra. We have this connection, which is going to be a generalization of the omega kz of Foucault's lecture. And in fact, here, now we are going to discuss base points. So what is a tangential base point? So we have here this general definition. So what it means in our particular case is that we are going to take the following configurations. We are going to take situations where you have, in Cn of C, so you have, so what we call Cn of R. Cn of R, so it's configuration of endpoints on R, and this is a disjoint union according to permutations of order points. So it's a disjoint union over sigma in Sn of you can say sigma times Cn plus of R. These are the positions where you have Z1 smaller than Zn on the real line. Okay, and so you have in fact. So this you can still take as base point because it's not really a point, but it's as much as good because it's a simply connected manifold. So in fact, you can this simply connected manifold as your base point, and in fact you have n factorial of them. Okay, so you can say this way I get n factorial base points, but it's still not good because in this situation you want to discuss a tangential base point. So in fact, you want to discuss different sectors of this. In fact, it's kind of compactification of this. And when you want these points to converge to be, so the notion of their closeness with respect to one another is important. So it's why you introduce the notion of a filter basis. Okay, filter basis here. And then, in fact, you define, when you compute monodromy, usually you compute monodromy with respect to a base point, which means what? It means that you want to compare solutions with respect to a given solution, which takes a value 1 at a given point. But here, in fact, you want to refine this notion, and you want a solution to have a particular asymptotic behavior according to this filter basis. Okay, so for example, what we have seen this morning is solutions which behave as z to the power a when z goes to 0. So this doesn't mean that the solution is equal to 1 at a given point. There is no given point where the solution is equal to 1. Rather, the thing is that the ratio of this solution to a given solution when z goes to some limit is equal to 1. So this is what we have here. So in fact, if you want to discuss tangential base points, the thing is that you need the following data. What the data you need is you need MB, so it's a manifold with simply connected. You need a filter basis topology of this manifold, and you need a function which relates to this data. So this is it. And given all this, you construct first of all a groupoid, which so the groupoid is given by so in fact the groupoid. So if you want to relate B and B prime, so you just put the homotopy classes of paths relating the two underlying manifolds. Okay, and the point is that the thing is that you get a representation for this groupoid from this, in fact, groupoid that you define here to this trivial groupoid using these functions. The important point is that you are using these functions in order to define this representation. And then in that situation, these lemmas can be generalized. And then, in fact, if you get J, connection with the correct properties, then you can generalize these lemmas to this setup, and then you get that this gives you isomorphisms. So in fact, when you pass to the multi-self completion, this is going to give you isomorphism. And here is the particular case that we examine. So here in this situation, you see that if you spell out the things, so in fact, the base set B that you are looking at is composed of, first of all, the permutations, but also a parenthesization. This parenthesization is going to tell you how the points, in fact, the bunch of points is going to infinity. And in fact, the solution, for example, in this particular case that you are looking at is this solution with a particular insubstitutive behavior, a solution of the KZ equation, which so it can be proved that such a solution exists. So okay, so this is the way this is done. Okay. And in general, it stops here. So in fact, you can do just this. So the point with braid groups that you have an additional ingredient. So this is just general formality up to now. The point is that there is an additional structure in the situation that we are looking at in this situation of configuration space, is that all this structure has an operatic. There is an operatic aspect to it. So the point is that, so here I am, so in fact, just historically, how the things started. So in fact, it must be said that, so in the Drinfeld theory, so Drinfeld theory has to do with associators and this isomorphism from, you pass from infinitesimally braided monoidal categories to braided monoidal categories. The point is that later on, it was realized that some operas control the situation, in fact. And in fact, associators can be expressed as isomorphism of operas. So this was realized by Benoit Fraisse. And so it's his it's a way of presenting things that I'm following here. So this is it. So in fact, first of all, the point is that in fact you have all these groupoids. These groupoids have an operatic structure. So what is the operatic structure? So in fact, already the aldehydes were present in Barnatan. In fact, so you have Barnatan. So in fact, these are the important names. In fact, after the work of Drinfeld, in fact, it was Barnatan who expressed it in terms of, rewrote it and understood it in terms of isomorphism substructures. And then it was Fraisse who put this in the formalism of operas. So in fact, all these are just rewritings of the same ideas, but in fact, it should be said that so it really adds something as a level of formalism. So it's yes. No, there is really something more in Fraisse and Barnatan. So. No, but co-completion is not a substitute for all this formalism of operas. So, okay. So, in fact, so first of all, let me say what we explain, what to understand. So, first of all, the thing is that what is the operatic structures of pure braid groups? So, the fact is that if you have if you have an element Pn, so you have an operation from Pn times Pk to P sub n plus k minus 1. And so you have n such operations. So what is the operations? So in fact, assume that I have a braid from Pn. Okay, and I single out one strand. And then I say that this strand, I take a braid from Pk, which k equals 2. And I say that I want to replace this strand with this strand here. So I'm going to double, for example, in that case, this strand here, and to follow what has been done here. Okay. So this is the operation. This is a substitution operation that you do in pure braid groups. Okay. And that's why the collection of pure braid groups has an operatic structure. Okay. And you can do the same at the level of infinitesimal braids. So at the level of infinitesimal braids, you have an operation like, for example, you are going to say, so in fact, you have Tk and Tn. And so the point is that if I get here Tij, I map it to Ti plus I, so image of I, so alpha I, alpha j. And then Tkl, T beta k, beta L. And so the thing is that I am taking a k, for example, so 1k by this map beta to 1 k plus n minus 1, and this 1n to alpha to 1 k plus n minus 1, the same way. And the point is that the image that you should follow is this. So you have these things here. This is the opening up that you have. So you have the old indices, and here you have the new indices. So you have the k indices here, and here the old indices that you opened up. So something like that. So there is this so these two operatic structures on both sides. Okay, and so in fact the point is that the the Kaiser connection that you can get in general, so it's compatible with this structure. So it's not just compatible for each n, gives you an isomorphism of two of these things, which is called hopeful groupoids. So you can say that this is categories enriched in coalgebras. Okay, but in fact, all these isomorphisms are also compatible when n changes. Okay, so it's that's the point. So here you have this. So it's why it's I say here that Kaiser connection gives rise to an element in ISO in operas of groupoids. So it's in fact this object is a very rich structure. It's each of them, for each n, this thing, usually it's a Hopf groupoid. And then this segment here, I write it to denote the operad that you have here of Hopf groupoids. Here you also have an operad in Hopf groupoids. And in fact, this ISO is compatible with the operatic structures on both sides. So that's why here you have an ISO in operads of groupoids. Okay. Okay. So in fact, the thing is that this operas in Hopf groupoids, in fact, it can be described. It can be described explicitly. Why? Because in fact, when you have a general such isomorphism, so in fact you can show, you can describe it explicitly. And what do you get? So in fact, for n equals 2, you are going to take to have so your operad here is very simple, and the other here also simple. And then what you have is you should say that you should take basically the sigma elements, the generator sigma 1 in B2. You are going to take it to exp of something times T12 times the permutation T12. So, and this element here, it's an element which should be invertible, so lambda. Okay, so here you get from this an element lambda in K cross. Okay, The thing is that if you have such an isomorphism, also it gives you, at the level of n equals 3, some image of the associator. And in fact, this image of the associator, so this element of the associator that you have to write the proper notation. But when we straighten things up, you see that you go to some element phi of T12, T23, which is an element in this Lie algebra, so X of the Lie algebra T3, okay, times the old associator. And this element here, it's also a new piece of structure that you have here. And in fact, you can reduce it. So this Lie algebra T3 is, roughly speaking, the same as the Lie algebra, free Lie algebra into generators. And so, in fact, that's why I write that, in fact, this data from n equals 2 and 3 gives you the two data of an invertible group element and an element, so in fact, exponential of Lie series in two free variables. Okay. And then, in fact, the question is, out of this, what are the conditions which should be satisfied by these two things in order to get an isomorphism of operas in groupoids? And in fact, sorry. So here, it's written here. There is an isomorphism of schemes, blah, blah, with M of K, and the differential of M of K, I think I have it somewhere. Sorry. Great, super. So in fact, the point is this. So okay, it's written here. You see. So in fact, here you see that the okay. In fact, the point is that you have this relation satisfied by this pairs mu phi, and in fact, this M of K defined by these conditions is exactly this isomorphism, this thing. The point is that this is a result of Barnett and Fraisse, that this set of iso of operas is the same as the set M of K, which is defined by these conditions, which were originally, which are the conditions satisfied by the Casio associator. So in fact, this scheme, this isomorphism of this set of isomorphisms is on the nose the same as this set M of K. So this has a consequence that it's namely that M of K is a torsor, in fact. As any set of isomorphism between two structures is a torsor over the group of automorphism of each structure, in fact. So in fact, this result here has a consequence that it's written here. This set here is a bitorsor over these two isomorphism groups, automorphism groups, and this is here the set of automorphism of operators of group X of this. This is an operator of group X, and this is another one. And here you have this. You can define this group. So this is called the GT groups. The pro-unipotent version of the Grothendieck-Teichmüller group that we saw yesterday, and this is GRT, the graded version. Okay. Now, in fact, the point is that in the same way as you can define precisely the set of associators, so explicitly using its action in n equals 2 and 3, you can do the same for this set, these automorphism groups. And in fact, you have here these inclusions, looking at what happens in degrees 2 and 3, and you have precise descriptions. And in fact, here, these are the precise descriptions. The group GRT is described here, and the group GT is described afterwards. Okay, and so you see here that for the group GRT, so it's a newcomer in this conference. The group GT is a known figure because we saw it yesterday with very similar formula. The thing is that these formulas here are to be taken in this Malchev completions of these groups. So pro-Unipotent completion of the groups, whether yesterday it was in the profinite completions. This GRT is a newcomer. So here it's the relations here take place. So take place, in fact, the two relations, in fact, they are known relations. So relations satisfied the groups, strangely enough, are the same as relations satisfied by the associator. So, for example, it satisfies, it should satisfy, one of the conditions is the pentagon condition. This pentagon condition is just the same as the pentagon condition of the associator, some other conditions. So conditions are written explicitly here. Here, these are our familiar relations from GT. And in fact, now it's good to discuss the precise connection between pro-Unipotent GT and GT from yesterday. So the point is that in Dreitfeld, it's explained that you can construct a pro-L analog of GT hat, replacing everywhere profinite by pro-L, and then GT sub L injects into GT of QL. So this is a precise connection between these groups. Okay, so this is in fact the way one can ideologically understand the construction of associators and the groups acting on it. Okay, I want to say, so it's good to mention that this approach is so it's costly, it's expensive conceptually, because you have to understand what are operas in Hopf-groupoids, and you have to read, for example, Fraisse, which is a thick book of 400 pages. So it's some investment. And in fact, there is a less expensive way of thinking about GT Lie algebras, which is the IARA approach. So in 2001, IARA wrote a paper in Israel Journal of Math, which is, and here is the account of it. And then in this paper, you can from this paper, you can understand the definition of a GT Lie algebra, which does not use those operas. Okay, so here is the thing. So here we have this group here in auto operas. This group here is just GRT. Okay, you can specialize for any n, and then you get an automorphism of group X at a fixed n for this here of group in, and then from this you get an outer automorphism for op algebras of this thing, of this UTN, which is the same as outer automorphism of Lie algebras of this Tn. So you have this Cohn-Dreitfeld algebra, and you have outer automorphism, which are SN invariant. And in fact, it lands into outer automorphism star, so which automorphism should take a Tij to a conjugate of Tij for any ij. So the point is that, in fact, whereas these families of outer Lie algebras are not connected when n changes. So the point is that you want to have a connection between various n's. The point is that at this level, definitely, you do have connection at the for various n's by the operatic structure, but it is costly, it's expensive. Okay, and here you lose connection. This is a particular n, and here at that point, this group of automorphisms, in fact, they are not related with when n changes. The point is that if you do this restriction, you request that Tij goes to a conjugate of Tij, and plus you add this SN invariant. Strangely enough, these groups start being connected with one another. You can, for example, in the Tn structure, in the level n structure, you can decide to kill variable. So when you have Tij, you will kill Tij whenever j equals n, for example. If you do that, you still consistently get an automorphism of the n-1 structure. And in fact, you can decide to kill either n or any other thing, the result will be the same. So you have a well-defined map independent of a choice of a marked index, from the level n group to the level n-1 group. That's the point. And in fact, the point is that you have this commutative diagram here that in fact GRT, I can see on the screen. Yeah, GRT here, in fact, so you have this canonical map from the level n group to the level n-1 group, and this map from GRT is compatible with both. Okay, so this is what we can derive from that, but the Yara approach rather is to study for themselves these groups so they can be studied. And what he can prove is that this sequence of groups stabilizes, and he proves GRT to be isomorphic to the stabilization of this. So namely, he proves that you have injectivity for n equals 4 and iso for, sorry. Yeah, so this map here is injective for n equals 4, and starting from n equals 5, it's an iso, in fact. And all these maps here are isos. So let me write on the blackboard. So that's the thing. So in fact, what he does is studying this sequence of morphisms of Lie algebras of groups or Lie algebras there. And in fact, what he proves is that here you have injectivity, and from there on you have equality. In fact, and you can prove you have a natural morphism from GRT1 to all of them. This he does, and he proves that you have equality there. So it's another way of thinking about this Lie algebra GRT1, which is maybe less expensive conceptually. So this is it. So okay, so I hope this clarifies a bit associators and GT groups and GRT groups. I think I am done. So thank you.